with the lowest gravitational attraction towards their planet. Then the main highlight of the research, which I called the revelation, and a few applications of it, a few drawbacks, and the usuals, which are conclusion and references. So let's dive right into it. So basically, compared to the inner planets like Earth and Mars, which have like 1 and 2 moons, Jupiter and Saturn have many, many moons. For example, Jupiter has 95 and Saturn has 146. And most of these moons of the outer planets are actually captured objects. And these objects can be asteroids or KBOs. So for reference, I've just put an image here. So the white dot in the center is the planet Jupiter, and all the circles, colorful circles, are the orbits of various moons of these planets. So while calculating the net effect of moons on a planet, we can ignore these small and distant moons because they have lesser gravitational influence on their host planets when we compare them to the giant moons. So this will not only make our calculations easier because we will be ignoring bunch of moons, it will also help us in various approximations. So how do we find these moons with the lowest gravitational force? So the most obvious way would be you calculate the gravitational force using Newton's law of gravitation, plot the data in a descending order, and the moon that is the end will be the lowest force moon, right? And we will just ignore it. So it seems very easy, but it turns out it is not that easy. So I'll explain why it's not easy with the example. With the example of Jupiter. So basically, we have Jupiter's data right here. So we'll see that we expect only one point to have the lowest magnitude, but in what we actually find is we get a series of moons which have nearly the same magnitude of force. So all these moons have nearly the same magnitude of force. So if I go on to select that this moon has the least magnitude of force, I would have to also ignore all the neighboring moons as well, because all of them have the same magnitude of force, right? So we cannot arbitrarily select a moon and say that it's the moon with the lowest force. We need a standardized way of selecting these moons. So the way to select this, to have the standardized way, one thing that we can use to our advantage are discontinuities. So one discontinuity is very clearly visible here, that is here. So what basically happens is, like if we go from this side, we see the points are continuous until we come here. So here we have a discontinuity. And why we're having this? It's because the data points on the left have way higher magnitude than the ones on the right, and hence they rise above. And hence these discontinuities show the sites where the magnitude of force is higher, and hence these are the ideal sites which can be selected for differentiating between higher magnitude moons and lower magnitude. So I'll just quickly summarize the technique which we use. So this is obviously not the entire data, but I have selected just for the demonstration purpose. So this is the data for Jupiter. So basically we have calculated the value of force and then taken ln of it, and we and put in a descending order. So basically these are points, right? So we can find the slope between these points, and the slopes are calculated like this. And what we can do after that is we can find the average value of these slopes, and this is right here. So what we can do is we can highlight all of those slopes that have the value higher than this average, and these higher than average value of slopes are special. So I can give them a special name. I can call them gaps. So why are these gaps or higher than average slopes special? They are special because they show the site where there is a more than average increase in magnitude of force. Hence, these gaps are the ideal candidate for selecting moons that have low magnitude. So now, once we have finalized all our gaps in the data, we can select the last gap, after which we'll have all the moons with the lowest force. So after this, I'll just introduce a bit of nomenclature, because saying the word least magnitude moon is a bit wordy. So what we can say is the moons that lie after the last gap, or the ones which have the lowest magnitude of force, can be called as insignificant, just because they have an insignificant contribution to their planet. And the moons which lie before the gap can be called significant. Now the nomenclature is a bit established. We can move on to the plots. So for Jupiter, the last gap is around here, and all the moons before the gap are significant, and the moons after the gap have the least magnitude of force and hence ignored and are the insignificant moons. So Jupiter has 79, and for Saturn, this gap is here. It's not very clearly visible, but it's somewhere here. So we have 35 moons for Saturn. And we'll now quickly discuss the number of significant moons for Earth. So Earth has only one body that influences it, hence Earth has only one significant moon. Whereas Mars has two moons which have nearly the same magnitude of force. You can see here, they have nearly the same order of magnitude. Hence both moons will have nearly the same magnitude of force, and hence both moons have an equal contribution to their planets, and they have equal influence, and hence both moons are equally significant, and hence Mars has two significant moons. Now I would urge you to keep a note of these numbers 79, 35, 1 and 2. They will come handy in the calculations ahead. Moving on to the main highlight of this work, that is the so-called revelation. So basically, the state of a planet can be described using few of these quantities, namely the orbit radius, which is the distance between a planet and the sun, axial tilt, which is the angle between the normal and the rotational axis, then the equatorial rotational velocity, that is the velocity with which the equator is moving of a planet, and number of moons, which is like quite self-explanatory, and then we have the diameter. So all of these quantities explain various physical phenomena on planets, such as the surface temperature, the wind speed, winds, in fact, seasons, weather conditions, etc. And all such phenomena are explained by these quantities. And it is well known, it's well established that all of these quantities are independent of each other. They do not affect directly each other. So, however, when you analyze the values of these parameters for the four planets, it actually comes across that these quantities actually are directly related. And how are they related? They are directly related by this relation. I'll just quickly show what this relation means. So here n is the number of significant moons, which we had discussed in the earlier slide. Theta is the axial tilt, v is the equatorial rotational velocity, r is the orbit radius, and d is the diameter. So when you substitute the values of each of the quantities in this, the obtained value of psi is same for all the four planets. So this table is also the proof of the so-called equation 1. And you can see that when I substitute the value of theta, v, r, d, n for Earth, Mars, Jupiter, and Saturn, we get the obtained value of psi to be nearly equal, right? It's coming very close. So this table not only acts as a proof of equation 1, it also shows that all these quantities are indeed related, and their relation is explained by equation 1. So this table is personally very exciting for me because it shows relations between quantities which we thought were independent. Moving on to the actual aim of equation 1, like why. So the aim of equation 1 is not to declare an planetary equation that is true for all planets across the universe. The actual goal of this research is to bring to notice or report the discovery of a pattern that the planets Earth, Mars, Jupiter, and Saturn follow, and exploit this pattern or the relationship to better understand the phenomena that occurs on these planets. So that's the basic goal of this entire work. Now, so basically we can simplify equation 1. So many of you might have noticed that the equatorial rotational velocity of a planet and the diameter are related, and they are related by this formula. And when you substitute it in equation 1, you can simplify it to obtain this, where T is the duration of the day or the rotational period. Basically, like for Earth, it's 24 hours, right? So equation 2, so this is equation 2. This is the simplest form of a planetary parameter relationship. Now, what is the importance of equation 1? Why am I talking about this? So the first point that I have already repeated once is it forms a relation between quantities which we thought were independent. So it starts entirely something new. It forms a relation between things that we didn't know of. The second point is it mathematically shows the effect of moon on its host planet. We've all been told that moons affect their planet. But this equation mathematically shows how does the moon affect a planet, or moons affect a planet. It also, the third point being, it also suggests that the change in one quantity can affect the other. So uh, if if somehow the r or the theta of a planet changes, we can predict the consequent changes in the other quantity. So this equation also suggests that. And also one pretty obvious fact is it shows a connection between the four planets. Moving on to few of the applications. So the most like the my favorite application would be, we can use it with the other known laws of physics such as Newton's law of gravitation or Kepler's laws of planetary motion, and we can make certain substitutions, and maybe we can obtain the values of gravitational force in terms of axial tilt, number of moons, or maybe something that was not used earlier. So it can show the dependence of quantities that we did not know of earlier. So that is one interesting application. The other application is, as I had mentioned this point in the importance. So basically, we can draw relations between quantities if we assume that psi is a constant for the planet. So basically, we can say that theta is proportional to r square and theta is proportional to t. All of such conclusions can be drawn using this equation. The other, another thing is, I had mentioned this point also, we can quantify the contributions of a moon to the planet, which we could not do earlier. And also, if one of the parameters of a planet are unknown, we can make it the subject in equation 1 or 2 and find its value if we have the knowledge of all the other parameters. And okay, so like all theories, even this is not perfect, and we have a few drawbacks. One of, not a major, but one of the drawbacks being the densities of all moons of Saturn and Jupiter are not known. So for many of the moons, we have assumed the value of the mass and the volume, and because of this, obviously with a certain error margin. So the plot that I have shown to you might slightly differ if somebody else makes the plot because of the error bar. The next point being, in equation 1 and 2, we have considered the average value of d and r. So we have not considered the value of r to be changing, which we know changes because of the elliptical orbit of planets. The third point being, this effort is now limited only to the planets Earth, Mars, Jupiter, and Saturn. So this is one of the major drawback, and this also includes the point that this equation as of yet has no theoretical or mathematical proof that can lead to the same conclusion. So that is one big point that is a drawback. And the next point be, we are not very sure that this equation was true during the early parts of the history of the solar system. It is very much possible that during the early chaotic stage of the solar system, this equation was not true. But so that is something that has to be dealt in the future. And the other point being, we can only assume psi to be a constant for the four planets. It is very much possible that in the near future, or in the future, as the solar system evolves, due to some change in the planets, it is very, very much possible that they do not follow this equation, and we do not get the value of psi to be a constant. So with that, I have completed most of my presentation, and I would like to conclude by saying what were the major points we had discussed. So one of the few points we discussed was the pattern that the planets Earth, Mars, Jupiter, and Saturn follow. And we also established a novel method of finding moons with the least affinity towards their planets. So these two things we discussed, and I feel that the future scope of this research is limitless for now. It's a big word, but because it's a fresh concept, and it's a new way to look at the working mechanism of planets. So as I said earlier, that if we use it with the other known laws of physics, we might come up with interesting conclusions regarding the fourth planet. So this is basically the entire presentation that I gave. instead of slides, if you want to read it in one concise, continuous paper, it is available as the preprint. So if you want to have a look at it, you can scan the QR code and have a look at it. And if you have any questions, we can have a discussion on it as well. So I'll keep the slide on for like 10 seconds, and then maybe we can have a thank you.
Yeah, in the meantime, so let me thank you for the very interesting talk. So thank you very much. And so please, we got several minutes for